Okay, it works now. Well, good morning, everyone. I am teaching algebra today, and I hope you all have the handout that I've sent to the group chat yesterday. So the first part, we'll be talking about polynomials, and then for the second part, we'll be talking about complex numbers. Okay, so in this lecture, let's start by talking about the definition of polynomials. So before we talk about polynomials, well, I hope you guys are familiar with, well, the few sets. For example, this one is the set of natural numbers, so 1, 2, 3, 4, 5, and so on. And this one is the set of integers, well, so including 0 and including the negative integers. And then we have the rational numbers, and then we have the real numbers. Well, and then afterwards we'll talk about complex numbers. But well, these sets are going to be our coefficients for what we call polynomials. So I will define this, a polynomial, and I would say in, let's say, a set, and then I'll write this. So where S can be any of these sets, but normally it's just Z, Q, or R, but I'll just allow it to be any set, is an expression or a function of the form a constant times x to the power of n plus another constant times x to the power of n minus 1, and so on until reach to the term where it's a constant times x to the 0. Well, that means it's just a constant term. So where a naught, a1, a2, dot dot dot, an, they're all in this set. So I think I didn't use this notation for the handout. I just talk about general polynomials in the handout. So I allow it to be any number. But if you want to be more specific, we can talk about polynomials in what kind, well, over what kind of set. Okay. So a polynomial is basically a function in that sense. It's a little bit more subtle than that. Normally we say polynomial is this expression with an x in it, and then we say it can be turned into a function by looking at x as an input. Okay, so these are the basic definitions. And just to settle some misconceptions, there are a few things that look like polynomials but are actually not polynomials. For example, this thing is not really a polynomial because it has infinitely many terms, whereas for our definition, a polynomial can only have a term with the highest exponent, like a finite exponent, and here, right? So this is not a polynomial. And well, other obvious things, for example, this is obviously not polynomial. Actually, these two are the same, but well, my point is polynomials can only take this form, and you cannot have negative powers as well. So these are all not polynomials. Not polynomials. But then you can create a lot of polynomials. For example, x squared plus 1, x to the 100 plus something, or minus something. So yeah. So that's for the basic definitions. And for a polynomial with the highest exponent n, we say that n is the degree of this polynomial. Okay. So let's say let this polynomial be fx. So we say that the degree of f is equal to n. Okay. So a few basic things that you should see. Oh yeah, one more thing. You also consider the zero polynomial, but the zero function as a polynomial, even though it doesn't really fit the definition. I mean, it does fit the definition here with a not being zero. But we normally require the first term to be, I mean, we have to require the first term to be non-zero, and then we can only talk about the degree. But we're also going to talk about the zero polynomial as a zero function as a polynomial, and so zero is also a polynomial. And for some reason that we would probably see afterwards, the degree of the zero polynomial, we normally say it's equals to negative infinity. Well, it makes sense to say it's degree zero, right? Because it kind of fits the definition here, but except for one thing. Well, if the degree is n, I must make sure that a sub n is non-zero, so it's like the leading coefficient. But in this case, it's not. So it doesn't fit any of the definitions beforehand. So we kind of need a new thing. And we just define this to be negative infinity. We'll see why later. Okay, we'll see why later. Okay, now, and a few other terms, for example, a root or a zero of f is just a number, let's say r, such that by substituting r into the polynomial, we get zero. So it's basically the solutions to fx equals zero. And also fx, a polynomial fx is monic if an is 1. Because if it turns out if the first term has coefficient 1, a lot of things will be nicer, as you'll see afterwards. So we give it a special name. Okay, so let's try the first few exercises. I'll skip the first exercise. That one's quite an easy one. So let's see. Is it possible that a polynomial of degree 101 to have a to have no real root? Is that possible? I mean, here it doesn't matter what coefficients I allow. I think this statement holds if we allow complex coefficients or real coefficients or rational coefficients. So can a polynomial of degree 101 have no real root? So the first term is x to the power of 101. Okay, maybe that's a harder question. I think the answer is no, because every real number has a real 101th root. But if it has, that means, oh, you mean the statement is no. Well, your reason, your statement there is true, but I don't think it proves this thing, because a polynomial of degree 101 can be something like 101 minus 7x squared plus x plus 1. That's also a polynomial. So how do we make sure there is a real root? And the answer is that this statement is false. There must be a real root, at least one. Okay, let's maybe let's not prove this yet. And we'll do the next one first. So the next one is a bit similar. So we change this 101 to 102. And is this statement possible? So I'm just asking if it's possible, not asking whether it's always true. Yeah, exactly. So good example. So someone said x to the 102 plus 1 equals 0 has no real root, which is true. And why? Because a real number to an even power is always non-negative. I add 1 is always positive, so it cannot be 0. Okay, but let's think about this. Well, so how do we draw this on a graph? It's kind of like this, right? I mean, it's not really a parabola, but I think maybe something like that. So there's this minimum point here. And to interpret that it has no real roots, I can say that this graph does not cross the x-axis. If it does cross the x-axis, then there's a real root. Well, this thing actually, again, is more subtle than it looks, because you have to really know what a real number is in order to understand that. But the rough definition here is that if it crosses the x-axis, it must be a real number there. Variable to the even plus real has 0. Yeah, exactly. I think it should be it should be strictly increasing or decreasing when approaching to a negative infinity or infinity, hence crossing the x-axis. Yeah. So yes, that's a valid argument. So what Heumann just said, well, oh yeah, that's a private message, sorry. Is that if we look at a polynomial with odd degree, oops, yeah. If you look at a polynomial with odd degree, the key thing is that this first term, the leading term, well, in very casual terms, we say it dominates when x is large. So when x is really, really large, the first term will kind of be larger than every single term after it. In fact, it will grow even faster and faster, because largest exponent. Yeah. And also you might ask, let's say, let's say I have x to the x squared plus 3x plus 1. And also let's say x, but then I have like 10 to the 10 to the 10 to the 10. So this is linear, this is quadratic. But for some reason, the quadratic still grows faster than this linear eventually. And well, you can say when x is equals to 10 to the 10 to the 10, then the quadratic is finally larger than the linear. And that, well, there's a nicer argument to this. So it's basically something like that. Let's take a look at fx over xn, right? Fx over xn, we'll get an plus an minus 1 over x plus blah 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 plus until a naught over x to the n. So why did I write this? Because if we take the limit as x goes to infinity, I'm sorry if you haven't learned limits yet. Basically what it means when x is going to a very large number. Well, this goes to an, right? The other terms go to 0 when x is large. Is the denominator, the denominator gets arbitrarily large. It gets arbitrarily close to 0. So that means fx kind of grows kind of grows similar to ANXN when x is large. So the other terms don't matter anymore. I mean, there's a slight deviation, but then my point is that they will grow the same way. Like we say it has the same growth order. And what does this tell us? This tells us if you draw the graph, let's say fx equals x to the 101 plus blah blah blah. So a lot of terms. Okay, it doesn't matter what the leading coefficient is. You can just adjust it. So what happens when x goes to infinity? When x goes to infinity, the first term dominates. It will go to infinity, right? So the graph will eventually be here. And when x goes to negative infinity, again, the leading term dominates. But then when x goes to a very large negative number, x to the 101 is a negative number. So the graph will kind of be here when x is a very large negative number. So it doesn't matter what happens in between. Like, we don't know what happens here. Who cares? The fact that as x goes large, the graph goes above the x-axis. When x goes large negative, the graph goes below the x-axis, means that at some point, it will cross the x-axis. Like here, I just drew a lot of them, but it can be just once as well. Okay, does that make sense? Okay. So again, this requires a little bit more thought if you're talking about this formally, because could you argue with derivatives too? Yes, probably, but I'm not sure how you can do it, because derivatives can help you determine the shape of that graph. For example, like where it has a turning point or whatever. Well, there are probably many ways to argue this. Okay, well, another thing, because just now I was saying, it takes a little bit more thought for this, because what if I just change the question to rational root instead of real root? So what's the difference between rational numbers and real numbers? Why does this statement not work if I change real to rational? It's kind of because what we call completeness, and a little bit about continuity as well. Yeah, square root 2 is not rational, but then how do we know a real number is everywhere on this line? And if it crosses at square root 2, it's not rational. But can we say that it crosses some number and the x-axis that it's not real? Well, the answer is no, because I don't want to go too deep into this thing. If you're interested, you can learn analysis, real analysis, or read up something about that. The very casual way of saying it is that a continuous function is something you can draw with one stroke and it's smooth. If fx equals zx, there must be a rational root. Okay, someone asked a very good question. So I assume that zx you mean like this, right? Is a element of this. So if fx is a polynomial with integer coefficients, so you said there must be a rational root when degree is 101. Actually not really. So the rational root theorem, as you pointed out, it tells you something different. The rational root theorem says that if you have a polynomial like that, where ai, they are all integers. If r is a root, is a rational root, then r must be plus or minus some factor of a naught. Wait, is it a? Yeah, and over some factor of an. Like that's what the rational root theorem says. But let's not prove it here as well, because we're talking about another topic now. But rational root theorem says there's no converse for this. Yes, there's no converse for this. So a rational root must come in this form. That means if you want to check if there's rational roots, we just have to check these candidates, right? But it doesn't guarantee us that there must be a rational root. In fact, in most cases, there isn't a rational root. And if there isn't a rational root, then this theorem doesn't tell us anything. It just says that if there is a rational root, it must be in this form. It doesn't say whether or not there must be a rational root. Yeah. So it doesn't matter if it's 101 or degree is something else. That normally, in fact, it's almost always. It's actually a mathematical way of saying almost always. So it's 100% probability that a polynomial normally has no rational roots. Okay, so let's not talk about the next two exercises. The one where you talk about the degree of the product of two polynomials and the degree of the sum of two polynomials. And because that one, I'll let you to think for yourself. It also explains why we define the zero polynomial to be degree negative infinity as well. Okay, where were we? So the next part, we're going to talk about the division algorithm. The division algorithm. So for positive integers, there's a analogous concept. So for example, if we have 10 and we have, let's give a larger number, let's say 102 and let's say 37, we can kind of write 102. Well, let's say this number is A, this number is B. We can always write A to be a multiple of B plus a number that is smaller than B, right? So 102 equals 37 times 2. That's 74 plus 28. So it must be some multiple of 37, and then I add a number between 0 and 36. In fact, it doesn't matter if A is larger than B or whatever. I can just sweep the two rows. I can just swap the two rows and say 37 equals 0 times 102 plus 37. That also works. It's a multiple of 102 plus a number that is smaller than 102. So, and it's unique, right? I'll leave it to you as an exercise to prove that it's unique. So the same thing can be said about polynomials, but instead of like talking about the actual size of the element, we talk about the degree of the element. So here's how it goes. If f and g are polynomials, I can always write f equals some polynomial times g plus a remainder polynomial. So these are all polynomials. We can omit the x, the bracket x, if we're not talking about the actual function itself. So f equals a polynomial times g plus r, where the degree of r is less than the degree of g. Hang on. Yeah. So for those of you who have learned polynomials at high school, you've probably seen this thing before. So there's something called long division. For example, if we have x7 plus 2x6 plus let's say minus 3x4 plus x cubed plus let's say like that. And we have, so this is our f, let's say, and let's say we have g equals x cubed plus 2x minus 1. Then there's this thing called long division, where you can find q and r in a very brute force fashion. In fact, it's probably the fastest way already, so I wouldn't say it's brute force. Plus 0x5 minus 3x4 plus x cubed minus 2x plus 1 over x cubed plus 2x, well, x cubed plus 0x squared plus 2x minus 1. then you kind of do this thing where you want to keep destroying the terms from the left. So x cubed plus x cubed times what will help you to cancel x to the 7, and the answer is x to the 4. So if there's x to the 4, then we can subtract x to the 7 plus 0x to the 6 plus 2x to the 5 minus x to the 4. We subtract, that will be 2x to the 6 minus 2x to the 5. And minus 3 minus negative 1, that's minus 2. Yeah, and then we bring down the next term and we start doing again. Oh, hang on, I forgot to put the x squared term. Okay, I kind of used a very complicated example, but I think you get the idea. 2x to the 6 plus 0x to the 5 plus 4x to the 4 minus 2x to the 3. And then you subtract, there will be minus 6x to the 4. And so on and so on, right? I think I will do it 3 more times until I get to this very end. And in the end, you'll get some remainder here that has a smaller degree than this. And then you'll get a quotient here. And so that will be your Q, that will be your R. So for those who have learned this in high school, you can see this already. But of course, this is just a procedure that helps you find Q and R. It doesn't really prove to you in any way that Q and R are unique. I mean, probably you can explain why it's unique, but you have to be very specific. I mean, you have to be very detailed about that. So basically, if you want to prove this theorem, where you can write it like that for unique Q and R, we can prove existence and uniqueness separately. In fact, a lot of proofs come in this fashion. So if you want to prove something is unique, well, first you prove that it exists, and then you prove that it's unique. So if you want to prove that that exists, we can use the long division procedure. But of course, if you want to write it as a proof, you kind of have to specify your exact algorithm of producing Q and R in this way. It's possible, but I think it's very troublesome. So I presented a different kind of proof using induction in the handout. If you're interested, you can take a look at it later. Well, I'm just gonna skip a few proofs for this class because first of all, you can read it after the class ends, and second of all, we might not have enough time. So I proved existence using induction, but on the degree of the polynomial. I think it's on the degree of G, I think, or on the degree of F apparently. And for the unique part, the uniqueness part, normally it's quite easy to prove uniqueness. So what we can do is that if there were two pairs Q and R, let's say Q1 G plus R1, and another solution Q2 and R2. If there were two solutions, we just have to prove that Q1 equals Q2, R1 equals R2. That means it's unique, right? So let's subtract them. This becomes 0. This becomes Q1 minus Q2 times G plus R1 minus R2. And notice that this thing has degree less than the degree of G. But then this thing has degree of G. So if Q1 minus Q2 were to be something non-trivial, like it's non-zero, a non-zero polynomial times G will be a polynomial with degree at least the degree of G. And they cannot add up to the zero polynomial. You can just look at the first coefficient. So therefore this must be 0. So Q1 equals Q2. And if that's 0, then automatically R1 minus R2 is 0. So that's uniqueness. That one's quite easy to prove. Okay. Okay. So what's the significance of this? So this division algorithm is the exact reason why we have what we call the remainder and factor theorem. So the factor theorem, let's take the factor theorem first. So if fr is 0, f is a polynomial. F is a polynomial. Then fx equals x minus r times some polynomial gx. So the backward part is easy to follow, right? If fx equals x minus r times some junk at the end, obviously if you substitute x equals r, it becomes 0. But then for the converse, where you say if r is a root, then x minus r is a factor, it might still be easy to argue, but it's not as direct as the backwards argument. So why this is true is because the fact that you can always, so in this case, x minus r is our g for the remainder theorem. We can always write fx equals some polynomial times x minus r plus a remainder polynomial with degree less than a linear one. And that means it's a constant, right? So basically what you're asking is, what must this constant be? And of course, if we want fr to be 0, that constant must be 0. And therefore, it's x minus r times gx plus 0. Okay, is this clear so far? So if r is a root, then x minus r is a factor. To prove this, you basically use the the division algorithm and then determine the final remainder, which is a constant. Okay, and a more generalized one is where if fr equals a, then fx equals x minus r gx times a. Well, same thing, you just use the division algorithm to prove this. So that's the remainder theorem. Any questions so far? Any questions so far? Am I going too fast? If I'm going too fast, please tell me. Like if you want me to repeat any part of the lecture, please tell me. Like any part, I will repeat in detail for you. Okay, if no, then right. So let's see the next one. The next one is quite important because it will be connected to the complex number lecture afterwards. So a polynomial of degree n cannot have more than n roots. So it doesn't matter whether it's complex roots or real roots or rational roots or integer roots or even positive integer roots. It doesn't matter. It cannot have more than n roots. And why is that? Because of the factor theorem. If r is a root, I can factor an x minus r outside. Yeah, I mean like any root, as in I allow it to be any sort of number. I allow it to be any sort of number. Like if I just say you cannot have more than n real roots, someone might pop in and say, okay, maybe there are a lot of complex roots instead. So the point is, this thing, you can add any adjective behind here. It doesn't matter. Yeah, exactly. Thank you. So x minus r not x minus r1. So if there's a root, I can factor it out. If there's a second root, I can factor it out again. So in the end, you must have x minus r1, the first root, x minus r2, x minus r3. And we keep factoring until we cannot have any roots anymore. So let's say we keep factoring until rk, and maybe there's a leftover polynomial, let's say gx, where gx has no roots anymore. So that's what we call a irreducible polynomial if you want. So this irreducible polynomial times a bunch of this. Well, obviously the degree is more than k, or more than or equal to k, the degree. Because there's already k factors here, k linear factors. And then times a non-trivial polynomial. So that means you can only have as much as the degree, as many roots as the degree is. So that's going to be quite important afterwards. Now, let's look at another result of this theorem, where a polynomial cannot have more than n roots. So I've also been quite sketchy here. The exact statement should be non-zero polynomial of degree n, but well, that case is obvious as well. So this one is about agreement of polynomials. So if, let's say, fx equals gx for n plus 1 values of x, where these two are polynomials of degree less than or equal to n. But then they agree their values for, let's say, n plus 1 values of x. So we are not given any information on the other infinite possibilities of x, just n plus 1 values. They agree. Then fx and gx are the same polynomial as polynomials. Well, that means fx equals gx for all x, basically. So why is that true? Why is that true? Why can't you agree for n plus 1 values of x if the degree is at most n? Roots define hx equals f minus g. Yes, exactly. So if we look at the polynomial fx minus gx, which is a polynomial, by the way, if you look at the definitions, this thing is 0 for n plus 1 values of x. That means it has n plus 1 roots, or at least n plus 1 roots. But this is a polynomial of degree at most n. So the only thing possible, the only exception to the previous theorem is that the polynomial is a zero function. So fx minus gx is the zero polynomial, and hence fx is equal to gx. Okay. So if you look at the polynomials with degree at most n, like if you have a collection of a collection of polynomials with degree at most n, there's a lot here. Well, if you collect all of them, and if you want to, let's say, have a polynomial where f1 equals some fixed number you like, let's say 70, f2 is 36, fn equals something else. I don't know. Let's say 2 or whatever. So you would know that there will be at most one polynomial that satisfies this thing if you only allow to choose polynomials from your collection. There's only one polynomial that satisfies this. Hang on, sorry. We need n plus 1 roots. So let's say f0 is 0 or whatever. So if you have n plus 1 fixed points, sorry, not fixed points, that means a different thing in maths. N plus 1 fixed values that we have to achieve, then there can be only at most one. Does that make sense? There cannot be two. if there were two, it will contradict the previous corollary. So is that okay so far? Okay, seems like everyone is okay. Right. So now the next section, we are going to prove that for this little problem that I described here, I said there will be at most one polynomial, right? So the next statement, the next section, we will learn a technique where we can assure ourselves that there is a polynomial that satisfies this: f0 equals 0, f1 equals 70, f2 equals 36, and so on. So there must be one, and therefore there's exactly one, because you cannot have two, you cannot have none, so there's only one. So the next thing, we're going to call it Lagrange interpolation. Or I think it's French, so probably Lagrange interpolation. So Lagrange interpolation is basically a procedure to construct a polynomial that passes through certain points, right? So let's say we want a polynomial f with degree at most 2, for example. So it's either a linear, a quadratic, or constant. But you want f pi to be pi plus 1. You want f10 to be 11. And you want I'll give any number. I don't know, 7. Let's say it's 8. So of course there's one polynomial that works. Well, fx equals x plus 1. So this is a case where we can guess the answer. And it's a valid guess because you are now sure that that's the only polynomial that you can have, because the previous statement says there are no other polynomials with degree less than or equal to 2 that satisfies this. So x plus 1 is the unique polynomial that solves this. I mean, that satisfies, well, including the first condition as well. So that's nice. That's nice. But what if we have a more complicated one? So let's say instead we have f0 is 7. f2 is suddenly pi, and f5 is 6. Then it's not so obvious anymore. So how do we construct it? So the trick here is to do something like that. We find, sorry, I have to write that condition here as well. Degree f is less than or equal to 2. So we're going to find. So the first step, find polynomials. F1, F2, F3. Okay, yeah. Someone said a very good thing. So yes, that's valid. So you can, for example, let fx equals ax squared plus bx plus c, because you know it's either a quadratic, linear, or constant. And then you just plug in and solve, right? You just plug in and solve. That's valid. That's absolutely valid. But we're going to do a procedure that allows us to kind of construct it for anything. In fact, I think if you want to prove that there exists one, I think you can do this argument, like some kind of okay, it's a little bit more subtle again, because you have to prove that there exists, because there are some of these equations that have no solution. Okay, we'll come back to that concept later. But let's just use Lagrange interpolation for now. So the first step is to find f1, f2, f3, such that, okay, first of all, the degrees are, again, almost 2, such that we're going to split this three statements into, well, the properties I will just separate it into F1, F2, F3. Let's see what I mean. So F10 is 7. F12 is 0. F13, oh sorry, that's a 5, sorry. F15 is 0. So it only satisfies the first one, and for the other two is 0. And how about the next one? F20 is 0. F20, sorry, F22 is pi. F25 is 0. F30 is 0. F32 is 0. Well, I mean, they're all 0 again. And then F35 is 6. And in fact, these are easy to solve for each problem here. Can we find F1? Can we find F1? So F1 vanishes. So vanishes means it becomes 0 at that point. So we say it vanished at 2 and 5. That means F1x must be x1 minus x1 minus x minus 2 times x minus 5 times something else. And since it's a degree at most 2, so that means it's a constant. So what should this constant be if F0 were to be 7? Well, F10 were to be 7. What should this constant be? 7/10. Let me check. Yes, exactly, 7/10. In fact, I'll just write it in a more technical way. So I'll just write it as 0 minus 2, 0 minus 5, and then a 7 on top. Yeah. So you mean, when you put x equals 0, these two will absolutely cancel with this. F1 doesn't exist. Well, F1 exists, right? Like that. So this is a polynomial that satisfies F12 is 0, F15 is 0, F10 is 7. Well, it is degree at most 2, so it works. Okay. Can anyone tell me the next one? F2x. What's F2x? So that's a 5, by the way. Well, the whole thing. Okay, fine. Yeah, you probably already know the whole thing. So it's like x minus 5, and as you said, negative pi over 6. Well, again, I write it in a technical way, so I'll just write it as pi over 2. Sorry. Yeah, 2 and then 2 minus 5. So that when you put x equals 2, these cancel. Okay, then the next one is easy, but same thing again. X minus 2 and then 6 over when you put 5, so that's 5 times 5 minus 2. Right. So we notice a pattern here, right? We notice a pattern here. So this number here, 7, pi, and 6, they just follow from what we want them to be. And the remaining part is just kind of like x minus 2, x minus 5 is kind of like the other two terms, and then divided by the expression where you substitute x as 0, so like the term that you want. Yeah. Does that make sense? Can everyone see the pattern here? Like if I give you another F4, like can you construct it immediately? Like very, very, very quickly. Okay, no one said no, so okay. So that's F1, F2, and F3. So what is the significance of this? The thing is, if we add up F1, F2, and F3 together, we get a polynomial that satisfies this, right? So we just add them up. Add. Well, that's basically it. F1 plus F2. So you just add these three polynomials together. Well, if you want to expand it, sure. But the point is, you always get a polynomial that satisfies this. So is that okay? So if everyone's okay, we're going to generalize it to the n variable case, which exactly is the same thing. It just needs to be written more carefully. So of Lagrange is if we have fxi equals yi for I equals, say, 1, 2, 3, blah, 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 until n. So it agrees at n values. And we see that the degree of f is at most n. Hang on. 3, sorry, n minus 1. And also xi are distinct. Xi are distinct. So how can we write f? How can we write that? So it's kind of like the sum of a lot of terms, the sum of actually n terms. So k equals, I'll put I, sorry. I equals 1 to n. So there are n terms, just like what we did here. Okay, and then let's look at how this looks like for n variables. So first of all, there's the blue number here. The blue number is just y, right? I mean like y1, y2, y3. So it's just, first of all, yi times like this whole thing. So how can we write that? How can we write that? Well, we can write it as the product. Okay. So like everything, like all I except, sorry, all j except I. Because we want to skip that term, right? X minus 2, x minus 5. It's kind of like x minus 2, x minus 5 over 0, 0 minus 2, 0 minus 5. And then the first line is where we omit the first one. The second line is where we omit the second one. The third line is where we omit the third one. Right? I mean the bottom changes, but I mean like the top bit. Something like that. So all j except I. And then x minus xj. And then xi minus xj. Right, so this all j except I, I'll just write it as j not equals to I. So basically j goes from 1 to n, but it skips I. It skips I. Right, factorization. Well, we can't really factorize this after we add them up, so that's like the best we can do. So this is Lagrange interpolation. Okay, it's 9 o'clock. Let's give like 1 minute for you to digest this. So remember, this whole thing is actually under the summation sign. So any questions? Any questions? Anything? I mean, when I say any questions, you can ask anything. Not necessarily the one that I'm currently talking about. Maybe something else previously, or whatever question. So is that okay? Wait, can you explain the x? Yeah, sure. So this part. Okay, so let's see. Hang on. Okay, suddenly the computer is lagging somehow. Okay, now it's working. So let's look at this. I'll write this in a nicer way. So f1, I'll write it as 7 times x minus 2, x minus 5 over 0 minus 2, 0 minus 5. So let's see, x minus 2, x minus 5. It's kind of like x minus 0, x minus 2, x minus 5, but then except the 0 term. Except the 0 term. So we have like 0, 2, 5. This play the role of x1, x2, x3 in the general theorem. So it's kind of like x minus x1, x minus x2, x minus x3. But then I skip x1. So that's why it's saying here, x minus xj. So j runs from 1 to n, but skips I. So I is, well, wherever we are, like in the first term, it's going to be I equals 1. It's going to be I equals 1. And the second term is going to be I equals 2. Then we skip the second one. So like this red term corresponds to this. Or in fact, I should say this red term, including this summation sign, corresponds to this. And this part, the blue part, is this bottom bit here. So if we had the ith step, so xi in this case is 0, then we're going to take x1, well, x1 is 0, minus x2, minus x3, and multiply them all together. So that's going to be xi minus xj. So xj here runs from 1 to n, but except the ith one. So like in this case, 0, 2, 5, right? 0, 2, 5 is our x1, x2, x3. Like for the previous example. So the red one is saying x minus 2, x minus 5. And then the blue one is saying 0 minus 2, 0 minus 5. And for the next term, f2 is going to be pi x minus 0, x minus 5, 2 minus 0, 2 minus 5. So 2 here is our x2. And we're going to have x minus x1, x minus x3. We skip the x2 term over x2 minus x1, x2 minus x3. Yeah, so yeah, I hope that's clear to you. Okay, nice. Okay, so back to, I forgot who said just now. So back to this one. So we can also prove this theorem about uniqueness, or sorry, existence, by using a substitution, right? Ax squared plus bx plus c. In fact, we can do this for the n variable case as well. But that doesn't really tell you the actual polynomial, unless you solve like a very complicated matrix. So f xi equals yi. So I'm gonna present a different proof for this, for the existence, but it doesn't tell you what it is. So what I'm gonna say is fx equals Okay, let's just write this in a more concise notation. K equals 0 until k equals n. N minus 1. And then a k x to the k. So I goes from 1 to n to n. So you can put in like, okay, a n minus 1 x1 to the n minus 1 plus dot dot plus dot 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 plus a naught equals to 0. Okay, and a n minus 1 x2 to the n minus 1 plus dot 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 plus a naught equals 0. A blah 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 a n minus 1 x n minus 1 plus dot 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 plus a naught equals 0. Okay. And then we want to solve for a n minus 1 to a naught. Oh, hang on. So how many terms are there here? There are n terms here. N terms, hang on. Something's wrong. Something's wrong. Oh, sorry. Y1. Y1, Y2, and then yn. Okay, that makes more sense now. So the first one saying fx1 equals y1, the second one saying fx2 equals y2, blah, blah, blah. And then we want to solve for the coefficients, right? We want to solve for the coefficients. And if any one of you have learned some basic knowledge of matrices and linear algebra, we can write this as this. Of course, if you don't know what I'm writing, it's okay. So this is just for fun. So x1 to the x minus 1, x2 to the n minus 1. So this will be a n by n matrix. Dot 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 dot. And then 1 1 1. Okay, so this matrix times a naught a1 dot 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 an. Sorry, an minus 1 equals to yn y2 dot dot y, sorry, yeah, yn. So what remains is to prove that this matrix has an inverse. And in fact, it's quite a theorem. There's this theorem that says that any matrix of this form where x1, x2 until xn are all distinct. Okay, there's a lot of new terms popping up, and you don't have to know this if you haven't done it. The determinant of this matrix will be, I think it's, if I remember correctly, it's the product of all possible differences xi minus xj. The determinant of this matrix is distinct, which in the case where xi are all distinct is non-zero, and hence it's invertible, and therefore we can just invert this matrix and find the coefficients a naught to an minus 1. This the theorem, if you're interested, if you know what I'm saying and you're interested with this, which is a very rare thing to happen. The theorem is, I think it's called I don't know what the thing is called, but this thing is called Van der Moon determinant. And I'm not sure if I spelled that correctly, but something like this. So yeah, it's a bit we have to be a little bit more scrupulous because not all simultaneous systems have a solution. And here we have to prove that this matrix is invertible. Okay, yeah. So that's that proof. And just get back to our main topic. So in fact, give me a few seconds to restart the whiteboard. Because it's getting really laggy now. Okay, so you guys can look at the next exercise. So fx leaves a remainder of 2 when divided by x minus 3. So times g1x plus 2. It's also it leaves a remainder of 1 when divided by x minus 4. So what's the remainder of, sorry, x minus 3, no, x minus 2, plus what? So what's the remainder of this thing? But there are probably a lot of techniques that you've learned if you've learned something like this before. What we're going to use is just pure Lagrange interpolation, because we know that this thing must be a linear function. Okay, not I don't think we even need Lagrange actually. This thing must be a linear polynomial. So Rx. And Rx just satisfies, well, we know that F3 is 2, F4 is 1. So plug that inside here, we get that R3 is 2 and R4 is 1. R3 is 2, R4 is 1. So what's the linear function that satisfies this? Well, I mean, sorry, linear as in at most linear. It can be constant as well. The degree is at most 1. So Lagrange, or you can just literally do the A plus AX plus C, MX plus C or whatever. But if you want to use Lagrange, we can just say this is 2x minus 4 over 3 minus 4 plus 1 times x minus 3 over 4 minus 8. So that's 2x minus 4 minus 2x plus 4 plus x minus 3. So that's minus x plus 1. So the problem is basically saying find a polynomial of degree at most 1 such that R3 is 2, R4 is 1. If you want to use this method, there are probably other methods, for example, like gx, writing gx in terms of x minus 4 times blah, and then substituting in. That works as well. Hang on. Wait, that doesn't work. R4 isn't 1. Give me a moment. Give me a moment. Anyone see the problem? Oh, sorry, this is 8 plus 8, right? Plus 8. So this is plus 5. Okay, that makes more sense now. Yeah. How do you know R3 is 2, R4 is 1? Okay, good question. So fx equals this. So if we plug in x equals 3, if we plug in x equals 3, this becomes f3 equals 0 because there's an x minus 3 here, plus r3. So f3 and r3, they agree at 3. So r3 is 2. And r4 similarly is f4, which is 1. This one comes from the remainder theorem. I mean, this one comes from this one comes from this. Yeah, okay, you're welcome. Okay, so that's one application of it. Well, the next problem, the next exercise is about well, loosening the problem. So let's say we don't impose the condition of the degree of f is less than or equal to n plus or n minus 1. So let's say we don't. We just let the degree be any number that we want. Okay. So then of course there will be infinitely many solutions. Right? Because if you want to agree at n points, I can just agree at those n points and agree at some other n plus 1 point and let the n plus 1 be anywhere. But say f naught x is the polynomial obtained by Lagrange interpolation. By Lagrange. So what are the other ones? So I mean, so like i.e. f naught x I equals yi for I equals 1 to n. So f naught is the one, is the answer that you get by using Lagrange interpolation. How about the other polynomials that satisfy this? So like if fx I equals yi for I equals 1 to n, can we kind of relate this f with f naught? And how do we do that? Can we write the most general solution? Basically, I'm asking. Can you write the most general solution? So that's what we like to do. We kind of try to think of generalizations for mathematical statements, and it will give us a lot of insight of what we can do. So anyone? Or at least anyone can suggest what's the first step we can do to simplify the problem. Like the first step we can do to simplify the problem. Anything, you can suggest anything. Subtract, yes, subtracting is good. So consider the polynomial fx minus gx. Minus f naught x. Then this polynomial has roots x1 to xn, right? This polynomial vanishes at all of these points because fx1 equals to f naught x1, fx2 equals to f naught x2, blah blah blah. So that polynomial itself has these many roots, and that's basically the converse is also true. If fx minus f naught x has roots x1 to xn, then fx is also a solution to our general problem. So nice. But then what does this tell us? This tells us that fx minus f naught x equals x minus x1, blah blah blah, x minus xn, times some leftover polynomial ax. So fx must be f naught x plus some product of all of these factors times a leftover polynomial. And let's check. This is what we get from the forward direction. Let's plug it back in. Does all polynomials of this form work? So let's see, fxi becomes f naught xi plus this thing, which goes away when you put x equals xi. So yes, so this is the most general solution that you can have. So once you get f naught x, you basically get all of them via this trick. We just add some multiple of the product of all of the x minus roots. And one thing to notice is that this thing has degree n. Sorry, is it? Yeah, has degree n, and f naught x has degree n minus 1. And this also tells us that there's only one of them that has degree at most n minus 1. Because if we just add some non-trivial factor, non-trivial multiple of this, we get a polynomial with degree at least n already. Okay, so is that fine? So any questions before we move on? Okay, if not, well, what is f naught x? F naught x is the polynomial that we get by Lagrange interpolation. So for example, well, Lagrange oh, this is a new whiteboard, sorry. Lagrange interpolation promises us a polynomial, right? Like fx equals the sum of k equals 1 to, or let's say I equals 1 to n, yi product of j not equals to I, x minus xi over xj minus xi. Sorry, x minus xj, xi minus xj. So this is the polynomial promised by Lagrange interpolation. And that's what I define as f naught x. So this is f naught x. Well, it is fx in the statement of Lagrange, but not in this problem here. I define f naught x as this the answer that you get by Lagrange. So basically it's fx in the theorem. But fx here I refer it to the most general solution. So basically you can say the solutions, well, the polynomial solutions to fx1 or fxi equals x equals yi, where I equals 1 to n, is fx equals this thing. So I just repeat everything. So this is my f naught x plus x minus x1, x minus x2. I'll just write it in a nice way. I equals 1 to n. So yeah, this is basically the full solution for any polynomial ax. Like all of the solutions to this condition. So is that clear? Is that clear? So I probably should use a different notation for this. I mean, probably I can just let gx be the most general solution. But here I'll just use f naught x because it's a fixed one, it's a single one. F naught x to be the one obtained by Lagrange. And given that answer by Lagrange, how do we construct the most general one? So fx must be exactly the same or the negative. Well, it's not a negative, is it? So like it's f naught plus this thing. It's f naught plus this thing. So yeah, fx must be exactly the same as f naught or f naught plus some polynomial in this form. But if it's exactly equals to f naught, that means a equals to 0. Is that fine? because Lagrange only gives us one, right? Lagrange only gives us one answer because the condition is that the degree is at most n minus 1. So Lagrange gives us this answer if the degree is n minus 1. But if we allow it to be any degree, including the ones with n degree, n plus 1 degree, and so on, the most general answer would be this one. So remove degree condition. Okay, so any other questions? Okay, if not, then let's dive into quite a nice IMO example. So it's a 2019 A5, which can be solved entirely using Lagrange, but you have to be very careful in what kind of numbers you want to use for Lagrange. Okay. So the statement is very, in fact, let's probably not let's not look at that problem first because it's quite hard. Let's look at a different problem that I can think of. Let me think of one. Let's say fx is a polynomial. Okay, so this problem is not on the problem sheet. Yeah, it's not on the problem sheet. F is a polynomial such that first of all, fk equals k factorial for, so this is not the general form, for k equals 1 to n. So the degree of f is hang on. Degree of f is me a moment. Degree of f is n minus 1, I think. Yeah. So what is, so find f0. Yeah, that should, well, n, f1 maybe. fn plus 1. So this is where you cannot let the problem deceive you, because fk is like k factorial for so many integers. It doesn't really mean that it will be true for all integers, right? So f1 equals 1 factorial, f2 equals 2 factorial, and so on. It doesn't really tell you anything about f0. So what can we do here? Sorry, degree of f is at most n minus 1. So let's try this problem. I'll give you guys a little bit of time. To try. Okay, f naught must be 0. Let's just see. Because I don't have the answer yet. I mean, we're gonna solve it together later. N equals 1. No, n is a fixed number here. It doesn't hold for all n. N is fixed. So I might as well say, I remove this and say this is 2022. I can do that. 2022, and then this will be like 2021. This will be 2023. Oh, okay, you actually, okay, n equals 1 implies fx equals to 1, n equals 2, fx equals to x. Okay, but how about 3, 4, 5, 6? Because that's where the factorial kind of pops in, right? Because you cannot really write a factorial in terms of a polynomial. But yeah, we're going to solve the general case for n. So let's use that. Consider the polynomial such that px equals x factorial. Well, the thing is, does that exist? So does that exist? Px equals x factorial. I mean, there's a few problems for this. Sorry. There's a few problems for this, right? Like, first of all, factorials are kind of only defined for positive, for non-negative integers. I know there's something called a gamma function, but then even if there's a gamma function, by the way, a gamma function is a analytic continuation of the factorial function. So it's like connecting the factorial points together to a smooth polynomial. But the gamma function itself is also not a polynomial. So there are no polynomials that satisfy px equals x factorial. So we cannot really use that. Yeah, right. In fact, there's another way to look at this. So why does this not exist? Because if, well, px grows with the order of, let's say, x to the n, right? Like if the degree is n. But then x factorial kind of grows like x to the x, actually. So it's like, well, you can see why, because that's x times x minus 1. It's kind of like x to the x over 2 times x. I mean, like, approximately. Can we find an f of the Lagrange interpolation, then that x equals 0 and x equals n plus 1? Maybe the factorials will cancel out. Yes, let's try that. So because, well, we just learned Lagrange, so let's try to use that. So here, k plays the role of xk. K factorial plays the role of yk. Okay, and this thing means, well, it's a very large hint that gives us to tell us that we want to use Lagrange. So fx equals not 1 to n, 1 to n. Yi, that will be I factorial. So that's yi. And then times the product of j, this. And this will be I minus j, x minus j. Because, well, xi equals I, remember. And of course, then yi equals I factorial. So let's see, plug in f equals 0, x equals 0, sorry. In fact, we can simplify the bottom bit here a little bit first before we plug in, because we want to find two values anyway. So I factorial, and the top bit is again this thing, x minus j. The bottom bit, now the bottom bit is a little bit sorry, it's a little bit difficult to see. So let's just write it out explicitly. So it starts from j equals 1 to n, but skips I, right? 1 to n, but skips I. 1 to n, but skips I. So 1, 2, 3, blah, 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 until n. But I minus n is kind of negative already, right? Because I is always less than or equal to n. So at some point, we must skip through 0. So 2, 1. And then we have the I minus I case, which we will skip. So that becomes -1, -2, so on. So this is the exact expression for the denominator here. Okay, anyone clear? Anyone not clear here at this step? Okay, so here this thing, let's write it in terms of factorials. I mean, there are some edge cases that kind of behave weirdly. For example, the I equals 1 and I equals n case. Like you may ask, do we even want to write this like that? And well, what matters is that after we kind of tidy it up into a very nice expression and see whether the expression works for a 1 and n, then that works anyway. So let's just write this here, x minus j over. So the positive parts, 1 to I minus 1, that's just I minus 1 factorial. Okay. And the second part, the negative parts, that's n minus I factorial times -1 to the power of n minus I. Right. So we just write it in terms of factorial, and then we can check it for I equals 1 and n if you're not convinced that those cases will work. And it actually works, yeah, it actually works for I equals 1 and n. Okay. Well, what can we do here? We can x minus j over n minus I factorial. Well, times negative, sorry, no space. Okay, this might be quite difficult to solve, but let's just try. Oh wait, no. Okay, maybe. So that's fx. So what's f naught? Or well, f0? Rewrite the whole thing. And then this is minus j, right? Okay. Well, this one's easy. What's this? This is just the product of all numbers from 1 to n, but skipping I. That would be n factorial over I, right? Of course, there's a lot of negative terms. The negatives, how many negative ones are there? There are n minus 1 of them. Okay. Now, a lot of things will cancel. So this one cancels. And this n and this n can cancel. So in the end, we have I equals 1 to n minus 1 to the I plus 1. and n factorial over n minus I factorial. Okay, this is also a very fun combinatorics problem. Or actually, this is like summers and products topic. But is this solvable? Okay, let's just stop here for a moment before we move on to solve this. In fact, I'm not sure if that's solvable, but it's probably solvable. So let's let you guys kind of digest what's happening here. What we're doing is we just use Lagrange interpolation and try to simplify everything that we can. For example, this bottom bit here, try to write it as factorials. Keep trying to write it as factorials, blah blah blah. Try to hope for cancellation. And yes, it does cancel into something like this. That's F naught. And is it possible that this can be solved? It should be. On the fourth line, where did the I factorial go? I cancelled it with this one. I factorial, I just cancel it with I minus 1 factorial. So we're just left with I. Yep. And this whole thing is just this. Sorry. Oh, wait. Yeah. This is the derangement. Oh, why are the green equal? Okay. Because the green is defined by the product of all minus j's, where j runs from 1 to n, but skip I, right? Skip I. So it's like minus 1, minus 2, minus 3, blah, 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 minus n. But then I skip I, so let's just divide by minus I. Well, the top bit is n factorial times a negative 1 to the power of n. The bottom bit is minus I, so therefore it's n factorial over I times this minus 1 to the factor of to the power of n minus 1. So the point is the products here can all be simplified into something nice, into factorials and whatnot. Okay. Now, this thing here is actually quite fun. It's something called a derangement. I think, did I talk about that last time for combinatorics, or was that junior? Does anyone recall I used the word derangement last time? Yeah, I think there's a symbol for that, but I don't really use it anyway. So if I remember correctly, this should be the derangement of. So if you write this out nicely, this is yes, last time combi class. So I'm just I was just confused whether I taught it in combi junior or combi beginner. So that's n plus. Let's start from the top and go down. N plus 1. Well, first of all, I can factor out the n factorial. I can factor out the n factorial. Okay. And then let's start from the first term. So that's 0 factorial. minus 1 to the n plus 1 minus 1 to the n over 1 factorial plus, sorry, yeah, all pluses. It's just the negative one controls the sign. Plus so on until minus 1 to the 2 over n minus 1 factorial. So this is minus 1 to the n plus 1 and then 1 over this minus 1 over this plus blah 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 plus minus 1 to the n minus 1 over minus 1 to the n. Well, you can just read what I'm writing. Sometimes sometimes I'm not reading what I'm writing. Why is it important? Where did you get the J from? The J is from the Lagrange interpolation formula. Like here, right? I just plug in yi equals to I factorial, xi equals to I. Like the blue substitution here. The blue substitution here. Because we want to find a polynomial that satisfies this, right? Fk equals k factorial. So they want to agree on these on these endpoints 1 to n. And then basically after this step, which is this is by Lagrange, everything afterwards is just algebraic simplification. So you can take your time to read every line and see how it simplifies everything. But the thing is, there's no new concepts here. I didn't use any complicated theorem or whatever. It's just that the first line is Lagrange, everything afterwards is just simplification. Well, until this last line, of course, where I have this. So derangements has this extra term. I'm just gonna write it as a derangement in terms of the derangement. So it's like this, and then that's a minus 1. So I plus 1 at the end. Yeah, I plus 1. So that would be minus 1 to the n plus 1 dn, which is a derangement for n plus 1. Or if you remember what I used last time, it's also the same as minus 1 to the n plus 1. And then the rounded function of n factorial over e plus 1. So yeah, well, I chose this problem to be, well, I chose this problem randomly actually, so I didn't know what the answer would be. It's actually quite nice. It simplifies to this. But I remember there are some nicer problems. For example, you can solve the same problem, but with k factorial replaced. You can solve the same problem with k factorial replaced with fk, the k Fibonacci number. Okay, the k Fibonacci number. Or you can replace it with 1 over k, I think. 1 over k. You can replace it with other things actually. I'm not sure if cos or sine k would give you a nice answer. But let's say 2 to the k, I think that also works. Oh, sorry, the Fibonacci number is where f0 equals 0, f1 equals 1, then fn plus 1, or n plus 2 equals fn plus 1 plus n. I think you can, it's possible to solve all of these problems if you replace k factorial with any of these. In fact, there are more of them actually. In the end, you just need to solve this very complicated sum. And sometimes the sum is in terms of the binomial coefficient, like the choose function. And sometimes it comes out like this. So there's a bunch of factorials. You have to be quite familiar with adding factorials, adding binomial coefficients. Maybe next time somebody will talk about sums and products in more detail. Oh yeah, this F0. I think Fn is something similar. Fn is something similar. Like Fn, I think you don't have this -1 term anymore. You don't have this -1 term anymore. And I think in the end you will get like n factorial times e. I'm not sure if you're going to have a +1 or not. But it's going to be like something like n factorial times e instead of divided by e. Because there's this term that's gone. Oh wait. Actually no. I think it's still n factorial over e. Well, you can try that yourself. But I think it will be a similar answer to this. Okay, that's actually well, not a very easy example. And we're running out of time. We can try the first few problems for exercises. So this is another trick that I haven't shown you yet, which is after you use Lagrange, you can kind of look at the leading coefficient. Look at the leading coefficient after you use Lagrange, because you know Lagrange is like fx equals some I yi product j not equals to I x minus x j over xi minus xj. So you know what's the leading coefficient? The leading coefficient it's just, well, this is just a linear factor, so I just change it to 1. So that will be the leading coefficient. Like for example, let's say you already know fx by guessing or by whatever means, you know that fx must be like x to the n. Let's say for example, or x to the n plus 1. Then you know the leading coefficient is 1, and therefore this thing, however complicated it seems, it must be equal to 1. So those kind of techniques you can use in the exercises. In fact, it's also what we use in the IMO example, as you can see. In fact, you can, well, I cannot really explain it now, but you can read that IMO example to gain more insight of it, because it's a really, really nice problem if you want to use Lagrange interpolation. Okay. So, any more questions before we wrap it all up? Why is x minus xj equals to 1? It's not equals to 1, but it's just the fact that we are looking at the leading coefficient. So, for example, if you have like let's say 2, x minus 1, x minus 3, plus pi x minus 3, x minus 2, plus 10, x minus 1, x minus 2. Then if you want to look at the leading coefficient, you just kind of, can you see like why the leading coefficient is 2 times 1 times 1 plus pi times 1 times 1? Like the leading coefficient means the highest power. Because it's a 1x, 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 1x. So the leading coefficient is just you add all of these terms out. So it's kind of like the same thing as you replace x minus blah into a 1. Does that answer your question? Oh, okay, nice. And also one more thing is that you have to note that all of these have the same degree. So they are all like quadratic. So that's why you can because if this were to be like x minus 1, then you can you would ignore this entirely, because you know the leading coefficient would not be x squared. In fact, I shouldn't say leading coefficient, because sometimes the coefficient of this is actually the coefficient of the coefficient, if this is 1 to n, this is the coefficient of x to the n minus 1, which can be 0 sometimes. That's why I shouldn't say leading coefficient. I should say coefficient of n minus 1, x to the n minus 1. And so this is wrong, sorry. Coefficient of x to the n minus 1. Yeah. My apologies. So any other questions? You can try the exercises. May I know how I got the answer at the last line? You mean the two circled ones? Or you mean the one with the red? Okay, the two circled ones. If you look back at the combinatorics problem, I mean the combinatorics handout last time, this thing is actually what we call the derangement. There is no nice form to write it out, I remember. I mean well, this is a nice form, I think. But like it counts the number of permutations without fixed points. But there's a nice proof as to why this is that, because well, there's this thing called e to the x, which can be written as 1 plus x squared x squared over 2 factorial x cubed over 3 factorial. In fact, this thing we will encounter later at the complex number topic. So this is e to the x. So if you put in x equals minus 1, that would be, I mean, you can write this more nicely as 1 over 0 factorial over 1 factorial. So this will be 0 over 0 factorial minus 1 over 1 factorial plus blah. Okay, and then you multiply by n factorial. So that would be n factorial and then blah, except the fact that it doesn't go just to n, it goes to infinity. So let's terminate this sum at the nth term. And then we add some leftover terms. So that will be kind of like n plus 1 factorial plus blah plus other terms. But this thing is really small, actually, really, really small. You can bound it by doing this. The absolute value of this is less than or equal to the absolute value of 1 over n plus 1 plus 1 over n plus 2 plus blah, which is also less than, strictly less than 1 over, well, this time this 1 over n plus 1 over n plus, I mean n squared actually, and then 1 over n cubed. You can bound this by like this, and this will be eventually less than 1 over 2. So this is an integer. This is a number less than 1/2. So you know that this integer must be the rounded function of this. Like that's the algebraic part of this derangement thing. Like how you get it's the rounded function of n factorial over e. But the actual significance of it is that it's a derangement, and you can look back at the combinatorics handout. Okay. Any other questions? It's 10 already, so if you don't have questions, you can leave now. Yeah, if you have questions, you can just ask me here. But you can just first of all mention that you have a question first, so I know that you are typing. Otherwise, if if no one says they have a question in the next 20 seconds, I would just assume no one has a question. Okay, looks like no one has a question. So I'll stop the video here, and I'll stop the recording. And I will see you guys at 11 then. Okay, goodbye.